Okay, so now let's just look at a bunch of example problems using this conservation of energy concept. So the tennis ball, first one, a tennis ball dropped from a height of 1.21 meters. What is its speed when it is 0.27 meters from the ground? And so the way I like to do these problems is I start by just simply writing conservation of energy, E before equals E after. And then I expand, right? And so K initial plus UG initial plus US initial equals K final plus UG final plus US final. And so I know there's a lot going on in this, but we can cancel things out based on what is happening. So we don't have a spring, so we can get rid of all of our US's. We're dropping a tennis ball, which means that our initial kinetic energy would be 0. So on the before side, all I have is the potential energy before. Now on the after side, I have to keep both of them because I'm looking for a speed, right? I'm looking for a speed which is in kf, but I'm not going to the ground, right? I'm going 0.27 meters above the ground. And so you could shift that 0.27 meters and then subtract out the subtract out 0.27 from 1.21 to get your essentially your delta H, right? But you can, and that would eliminate UG final, but I mean that's 6 of one, half dozen of the other. Okay, and so now what I'm going to do is substitute in my equations. Okay, now one thing you notice, they don't give us the mass. And oftentimes in these problems they don't do that because mass, as long as it doesn't involve a spring, will always cancel out. And so I end up with GI equals 1/2 V squared plus GHF. I can get rid of the 1/2 by multiplying everything by 2. Right? So now this really just becomes, after this point, it just becomes an algebra game, right? Working my way down to what I'm looking for, and it's going to be that V squared, okay, or essentially that V. So now I'm going to subtract over the 2GHF, and I'm going to, in one step, I'm going to factor out the 2G because G is always constant and 2 is a constant value. And so my last step would then be to take the square root. So the final speed would be the square root of 2G times H minus HF, which is consistent because there's another way to write conservation energy to say that the change in kinetic energy is equal to the negative change in potential energy. And you could see that at this point in time here when you write this 2GH minus HF. And now all I do is plug in numbers. So I would say square root of 2 times 10 times 1.21 minus 0.27. And so you would do the square root of, plug in my calculator, square root of 2 times 10 times 1.21 minus 0.27. Make sure you're using parentheses and so forth if you're going to try to stick it in the calculator in one shot. And so it would have a speed of 4.34 meters per second at that height. Okay, if I go down further, if I go all the way down to 0, I'm going to have a greater velocity or speed. Alright, next part says 2 blocks A and B slide down 2 different frictionless ramps from rest. Block A's ramp is much steeper than Block B's. Block B's mass is about half that of Block A. The centers of mass of both blocks begin at the same height above the ground. Which block has more kinetic energy at the bottom, and then which block has a greater velocity at the bottom of the ramp? So if I'm drawing my picture, right, so Block A is much steeper than Block B, right, the ramps. They're leaving from the same height. Okay, they're saying that the mass of B is 1/2 that of mass A, so B is going to be smaller. And so which block has more kinetic energy at the bottom of the ramp? So that would be Block A, just by the fact that its mass is greater, Sorry, it's a little sloppy. Right, so mass A is greater than mass B. So one thing to note that the individual pieces have a factor of mass in it. Okay, but for part B, which block has a greater velocity at the bottom? Well, the velocity or speeds, they will be equal. Right, and why is that? Because they're being released from the same height. So as you saw in the previous example, the masses cancel. Right, so through the formula, the masses ultimately cancel, and it would leave just a factor of essentially your speed would be the square root of 2gh. And notice there's no mass in this. Okay, they like to do this for multiple choice questions. Talking, essentially, part A, which block has, the question would be which block has more kinetic energy, and it would say like A, block A, B, block B, block C, or C, same kinetic energies, D, can't determine, or something like that, right? And so you would just choose block A. You don't have to really prove it. All right, so the next question involves a spring, okay? And really, you got to treat this into two parts, and really the parts get separated right here, okay? Actually, not there, sorry. They get separated right here, right? Because the first half, and what happens is the final velocity from the first will become the initial velocity of the second part. Okay, and so again, we start with our process. EB equals EA, right? Potential energy before equals potential energy after. And then I write all my energies. Right, and so now I'm going to cancel. And this one you have to, so there's going to be no height difference because the road is level. Right, so this is a level road. So there's going to be no height difference. But I do have to factor in the spring. When I stretch the spring all the way back, it's only got that stored energy, and then once the car comes off the spring, it's no longer there, so it's going to be kf, right? And so 1/2 kx squared equals 1/2 mv squared, and now it becomes an algebra game. Cancel those. I'm going to solve this for v, so it's going to be the square root of kx squared over m. Okay, and now I can plug in my value. So my spring constant 250. You have to convert that 4 centimeters, and the mass of the car is 0.100. Right? They may give you that mass in grams, or so it'll be 100 grams. So then I do the square root of 250 times 0.04 squared divided by 0.100. And I get a speed of 2 meters per second. Now what happens is that 2 meters per second becomes the initial velocity, but as it goes into the hill. So again, I start with EB equals E after. Write all my kinetic energies down, or my energies. Ultimately, like here, you would see there's no spring, so you could technically not write the spring piece. I just like to write all of it and then cancel. Right? So my spring is no longer involved, even though it is there. It's no longer involved. I start at h equals 0, right? And so on the before side I have ki, on the after side I have kf plus ugf. And so I would have 1/2 mv squared, it would be initial squared, equals kf, so 1/2 mv final squared plus mgh. And so I'm going to solve this, right? And so now you can see now it becomes my algebra game. And so I can multiply everything by 2, so I get vi squared equals vf squared plus 2gh. And I solve it for vf, so vf is going to be the square root of vi squared minus 2gh. And so vf equals the square root of 2 squared minus 2 times 10 times 0.18. I'm going to write my answer over here. So my final velocity would be the square root of 2 squared minus 2 times 10 times 0.18 and that would be 0.63 meters per second. And it makes sense that this is less, is because now part of it is going to, right, part of the energy is going to our potential energy. All right, so we have one more example, and this is a very heavy example, and I got this one from the AP Classroom site. And so we're looking for the minimum starting height, this h, needed in terms of r, so in terms of the radius of the circle, for the roller coaster to make it through the loop without falling. B, how would your height be affected if we increase the mass? C, how would it be if we doubled the radius of r, the radius of the circle? And then if we took this to the moon, right, what would happen, right? And then if the tracks were not frictionless, now what modifications could be made, right, for the cart to get through the loop-to-loop? Now the first thing though is we need to know how fast is it moving in the loop, right, or a relationship for that. And we're going to have to apply Newton's laws, right, with our unit 3, right? And so at the top of the loop, it would have a normal force, a normal force in, a weight or down, right? But this is in a circle, so my positive is inside. So when I sum the forces, I would get Fn plus Fg equals mv squared over r. But to make it just through the loop, you would not have a normal force, okay? And so essentially what that means is that your weight would have to equal your centripetal force, or because that's 0, that your acceleration through the circle would have to equal your acceleration due to gravity, which means you would have the square root of gr would be the speed at the top, okay? And now we're going to use that for our energy. So part A, we're going to start with our E before equals E after. Again, we're going to write down our energies. So UG, KI plus UGI plus USI equals KF plus UGF plus USF, right? Cancel things out, 0, 0, or not important because there's no spring. Roller coasters start from rest. Okay, and I can't cancel anything else out because I have a speed at the top, right? Because this is the top of the loop, right? And this is the hill. And then I'm going at a speed at the top of the hill or of the loop, and I'm trying to figure out. So I have UGI equals KF plus UGF, and now we play our algebra game. So MGH equals 1/2 mv squared plus mgh, right? So h, in fact, if I plug in, okay, this is going to be mg times 2r, right? Because I'm at a height of 2r at that point. And so you can see here's our game again. We don't have to worry about the mass, okay? And then now I can substitute in my speed that I found over here. So you got 1/2 times the square root of gr, and that's going to be times 2gr, or plus 2gr, and that's going to be squared. And so if I square root, that goes away. So it's h equals 1/2 gr plus 2gr. So I would have to start this roller coaster at 2.5. Oh, sorry. And I still have this g running around, and each one has a g factor, so that would cancel. So that actually gets this away. So let me clean that up a little bit. And so that'd be 2.5 r would be the height that I would have to release this from. So 2.5 times the radius of the circle. So if I had a 1 meter circle, this would have to be at 2.5 meters. If I have a 10 meter circle, it'd have to be at 25 meters. Okay. Now the rest of these are more conceptual based, right? So B, how would increasing the mass of the roller coaster affect the minimum starting height needed? So remember, masses cancel, so no effect, right? So notice in here, there's no mass factor, so there would be no effect if I doubled the mass of the object or of the cart. C, how would doubling the radius of the loop affect the minimum starting height? So height is directly proportional to radius, right? And so what that means is if I double the if I double the radius, right? And so if I do our factors of change and say h equals 1 times 2, right? So what am I have to do? I'm going to double the height. So if I go back and look at my equation, that means if I double the height, my initial hill would have, or if I double the radius, my initial hill would have to be 5r, right? Because I have to double that initial height. Part D, if we were to take this to the moon, how would that affect the minimum release height needed? So the moon, g moon, is less than g earth, but notice in my equation 2.5r, there's no g factor, right? So what does that mean? There's no effect if I did this on the moon, and there's no effect if I really do this on any planet. Okay? And then E, what modifications would I have to make if the tracks were not frictionless, right? Because we're assuming frictionless. So the friction takes away from the energy, right? So friction would decrease the energy. So it means I have to find a way to increase my energy to that point. Well, I would increase my, I would have to increase my H. Okay. The other thing you can do is something along the lines with the loop. But if we keep the loop the same, right, we would have to increase our H because friction will decrease energy. And I forgot the word energy here. So I need to find a way to get energy back, right? To offset the balance, right? To offset the loss due to friction. And so what I do, I increase that H, right? And so like doubling it may do that. Tripling it or quadrupling it may also do that. All right, so we're about ready to finish. So we got just a quick little section on power, okay? And so we'll do that in the last video.